we're going to go ahead and take a look at number 99 from section 9.1, radical expressions. The question asks us to go ahead and graph the following function, f of x is equal to the cubed root of x minus 1. And what I want you to note before we begin is that the minus 1 is outside of the root. Okay, if you're doing this by hand, you might want to kind of break your radical sign a little bit just to let you know where it's closed off. Okay, so to begin, let's kind of go ahead and investigate the parent function. So the parent function is where we strip away all the bells and whistles. And by bells and whistles, I am referring to any horizontal or vertical shifts, so moving left or right, up or down, or any sort of reflections. And we had studied all of those in Chapter 8, Section 5. So let's note the general shape, and we'll do that first by creating some points. And I'm going to select the following x values, and these are on purpose. Can you think as to why I might have picked -8, -1, 0, 1, and 8? There is a reason. Why didn't I pick 2, and why didn't I pick -3, for example? Well, the reason being, if we kind of take a look and do f of -8 is going to be equal to the cube root of -8, because we have learned how to work with function notation. The cube root of -8 gives us -2. The cubed root of -1 gives us -1. The cube root of 0 gives us 0. The cube root of 1 gives us 1. And the cube root of 8 gives us 2. So I selected all of these values because they are perfect cubes, and therefore I'm going to get a nice integer value out when I take the cube root. If you were to pick anything else, you would get run-on decimals. Okay. So if we were to go ahead and graph this, set this up, and I will graph this in a purple. So our first point is at -8, -2. Second is -1, 1. Third is 0, 0. Fourth is 1, 1. And then our other point is at 8, 2. If we connect this, note that we kind of have a snake that slithers horizontally, very similar to your cubed function, your cubing function, excuse me. So now we know what the general shape is going to be. Let's focus our attention back on the -1 in the original function that we're supposed to be graphing. Note that, again, it's outside, so this is going to be what kind of transformation? Hopefully you were saying vertical, okay? Remember, if we add or subtract a number that is outside of the function that we are looking at, then it's a vertical shift. So we are going to be moving up or down. And in this case, remember that vertical shifts are truthful. So since I see a -1, this is telling me that I'm going to go down 1 unit. Okay? So if I'm moving down 1 unit, that means that I am traveling along the y-axis, so my y values will be affected. So in order to exhibit this change of moving down 1, I'm going to subtract 1 from all of my y values. So my new set of points will be -8, -3, -1, -2, 0, -1, 1, 0, and 8, 1. Note here that my x-coordinate, or my x values and my coordinates match with the x values that I have from my parent function. And again, this is because I'm only moving everything down 1 unit. Okay, if I were moving things to the left or to the right, then I would invoke some sort of change onto my x values. But since I'm not moving to the left or to the right, my x values stay the same. So with these new coordinate points, we will go ahead and graph this. And we'll note this in like a hot pink. So here's -8, -3, -1, -2, 0, -1, 1, 0, and then transforms our shape. So note that our shape didn't change. It's still that snake shape that slithers horizontally. But note that all the points, if you compare them to the graph on the left, they've all moved down 1 unit. Okay, so now we can go ahead and start noting the domain and the range for our function that we have in the hot pink. Okay. When looking to see what x values we use, please note that I did put arrows on my function, so that means that this is continuing to move indefinitely both off to the left and off to the right. So that is why we can say that we're going to use all the x values, or we are going to go from negative infinity to positive infinity. Please note also that, for example, on the left, my graph is continually sloping downward, okay? And then if you move to the right, it's continually moving upward. There's never going to be a point with the cube root function where it's going to level off. So because it's continually going down and continue to the left and continually moving up on the right, I'm actually going to use all of the y values eventually. It's going to be a very slow process, but I will use all of the y values to create coordinate points. So that's why I go from negative infinity to positive infinity for the range. So that's actually something that's kind of nice. Think about it as well. If you were to graph any other cube root function, if you were to transform it by reflecting it, moving it to the left, to the right, up or down, or some combination of those three, would your domain and range ever change? Would you ever have an instance where the domain and the range would not be negative infinity to positive infinity? Think about that, and if you guys have any questions, please come see me.